Hello, I am Tony. My set was A. I'll be discussing about each and every question thoroughly. The first one was given an AVL tree storing numeric values, design an algorithm to return the efficient sum of all values within a given range LR. So for that I've already took a AVL tree there and left right range as 10 and 20. My pseudocode I wrote for that is this: if node equal null, then we'll return 0, and if not, so we'll check both left and right. Suppose if the node dot value is greater than the right range, then it will go in the left direction. If the node dot value is less than the left range, then it will go into the right direction and add this up, and afterwards I will send back the parameter again. Else if the node value is falls under the range, then I will add the node dot value, and both left and right will be going into the this function parameter again. We'll call that function again. Okay. For that, the 15 it falls under the node dot value, so we'll add this up. Then again this 10 also falls under the range, so we'll add this up too. And the 20 also falls under the range, so we'll add this up too. But here the left value is node dot value is less, so we'll not take it. We will take the 12. This doesn't satisfy this two statement. Then again this 25 doesn't satisfy this range. A leaf dot value node dot value dot r, this doesn't satisfy that, so we'll take only 18. So the sum will be like 10 plus 12 plus 15 plus 18 plus 20, which is 75. Now why the time complexity is order of log n, as we don't have to traverse all the edges. Like we can decline this one and we can also decline this one, so the order is not order of n, it's order of log n. The follow-up section, how my upload skill if each tree update must propagate features for downstream ML models. So basically what a tree update means. A tree update means that I'm inserting a new value, or I'm deleting a value, or I can change an existing value. That means updating the value. If in an AVL tree, that it may also trigger rebalancing, but the main idea is the data is changed, so that is occurring the tree updatation. Suppose like if my user 10 is changed into 12, then the value is changed also, so the old sum 75 will be gone and the new sum will be 80. Now if the sum is used as a feature in a machine learning model like a recommender system, then that suggests products based on total use pending, then that model must be notified that the feature has changed. So that's why we needed a feature propagation. For example, like in here, each node could not just store its value but also a subtree sum, the sum of all values in the subtree. Suppose in node 10 the subtree sum will be 5 plus 10 plus 12, which is 27. For node 20 the subtree sum will be 20 plus 18 plus 25, which is 63. Now if a node 10 changes from one value to another, similarly it will trigger something like a feature update. Suppose I have a user group like A B C D, so my user group A, then the change sum will also be passed as a parameter. So basically we are pushing the updated feature sum min and vector to downstream ML model. So what this is doing, after updating the nodes, I have to revise a feature that adds up. So if the model uses features like purchases or total rating, so I must update that total whenever a node's value is changed, so it must be in real time. Then again, if there is like a recalculate an embedding vector or mean, That means the model uses average or learned embedding. Those also needs updating. Also, there can be like a modification messenger to send. Finally, after recalculating all the feature and the embedding vector, the you I have to push the updates to the machine learning pipeline. For example, feature store. So this ensured that machine learning model always works on the most recent and real-time data. So basically the core idea is when I have millions of users and frequent data updatation, then I cannot recompute everything from the scratch. So to scale it efficiently, I have to store the augmented data, then update only the affected pairs, and and that's how AVL tree can be helpful for that. For the question 2, suppose you must store and retrieve large model weight files distributed across a database. Explain how a B tree supports first search and insert operations at scale. So basically a B tree is a special type of balanced search tree that is optimized for storage on disk or databases, where reading and writing is slow. Unlike a normal binary search tree, this B tree can hold multiple keys and children, not just one. So basically, like here we can see that 18, 20, 25 multiple keys are holding. We have created this one as B tree. So B tree is shorter and wider, so there are less edges. So we have to traverse less, and the time complexity is much higher than a regular AVL tree. Suppose how a B tree helps in storing large model weights. Basically, B tree is storing in layers. Like suppose I have layer 1, and there I have a huge weight chunk 1, and then I have layer 2, I have huge weight chunk 2, and then similarly I have like rest of the layer and layer n weight chunk n. So what I need to do, I can quickly find the weights for a given layer. So B tree helps in efficient key search. So as it stores values in key and pair, so the B tree can quickly find that key in order of log and time. Then so in B tree, the insert operation, the update operation, the delete operation, all are like order, log and time can hold it, because it's reducing the height of each tree. Also this can also like for this structure, this is reducing the disk IO operation. Since one node of B tree is storing many keys, one disk read brings in multiple potential matches, so we have to do fewer total reads and the faster performance. So in large model, this works efficiently even if you have millions of layers or weight files, because height increases very slowly with more data. So to sum up the full scenario, basically a B tree is a self-balancing multi-level search tree optimized for disk-based data storage. As such, it reduces the number of disk reads by storing multiple keys per node. The searching, inserting millions of keys like model weights can be similar features, becomes fast, scalable and efficient, typically in order of log and time that I have discussed before. Now for the follow-up section, we have how does this apply to feature vector lookups in recommender system. Recommender system is basically a system where we use the past based on past behavior, we recommend something. Like it can be like suppose like Netflix, if you saw some movies like sci-fi, then based on your past activity in future terms it will recommend you movies. So every user or item here has a feature vector which represents its characteristics in numbers, like embedding. Suppose I have took set 3 users and their feature vector. When my model wants to recommend items to user 103, it queries the B tree index for key user 103, gets the feature vector quickly and feeds it to the model. So B tree fits perfect in here, as retrieve a user or items feature vector is fast, update vectors as behavior changes, like insert update is also fast. That's basically a key value retrieval. So if we consider this in time complexity, searching for a key takes order of log n time, updating a key also takes order of log n time, and so also deleting also takes a similar time. Now coming to the main thing, like why it's useful at scale. Like large systems like Netflix, YouTube, that I talked about previously, like there are millions of users and items, feature vectors stored on disk-based databases, and constant updates are needed as new behaviors coming. Like suppose you've seen something new. So using B-tree keeps retrieval time small, like logarithmic, reduces the disk accesses, like the IO operations, allows fast updates when feature vectors are retrained or changed. That's why feature stores and vector databases internally often use B-trees. In to sum up everything, it benefits in fast lookup, scalable storage, and efficient update. So in recommender system, B-tree is used when feature vector to look up. So that's all from this question. Now I'll be discussing about the question 3, which is outlining an algorithm for finding a minimum spanning tree MS tree in a distributive system. For that, first we have to know what is an MS tree. I have already wrote it down here. Basically, MS-tree connects all the vertices and no nodes are left out, and there can be any cycles, like no cycles, and has the minimum total edge weight possible. So from this graph we'll be going to get this MS-tree graph that I'll be discussing later. So for that, the algorithm I have choose is Barufka's algorithm. Basically, Barufka's algorithm is best fit for here, as Barufka's algorithm find its cheapest edge locally and merge results in parallel, so no global coordinations is required, making it ideal for large scale distributed systems. Suppose like we have thousands of sensors, like as I have to discuss about this in follow-up sections. So it's spread across a large region. So why Barufka is best fit for this, as in each region sensors find their cheapest local links, then these links are merged gradually. Finally all the regions are connected from the global MS-tree, so it's super efficient. Now to discuss about how this Barufka's algorithm work, I'm going to talk about the pseudo code that I've took here. Basically, for first, there we need a graph and that has vertices and edges. We start with an empty set MS-tree, as I can see it in here. As long as the graph has more than one component, like in recursion process we will be traversing it, we keep repeating the process because the goal is to merge all the components in the connected MS-tree. Then again, as here we can see that we are creating an array named chipset to store for each component. It's the cheapest outgoing edge, like the smallest weight for each component. Now for each edge we are computing if component compo u, that means the component u is not equals to component v, that means this is not the similar component. If it's a different component, then we can go through, but if it's not, then it will be like a loop, like this is traversing itself. So we cannot take that as in MST, we're not considering loops. So in here basically we are checking for the component u of this age has a similar weight than the current cheapest one. If this age has a similar weight than the current cheapest one, then we update it as the new cheapest age for that component. Similarly, we are doing this for the component v as well. After scanning all the ages, we go through each component one by one. If a component I has the cheapest age selected, we take that age, and if they're still separate, we add this age to MST. Then we merge the two components connected by that age, so they now become the one combined component, and finally we are returning the MST. So here the time complexity is order of e log v, because we scan all the ages in iteration order of e, and the numbers of components roughly halves each time, like log v. So if we now go through our graph, like how we are getting the MST, as we have seen before, that we are locally calculating each node. So for 1, I can see the minimum weight is 1, which is connecting the component 7. For similarly, like 2, it's 4, which is connecting again 7. Similarly for 3, it's 9. For 4, it's 3. For 5, it's 17. So like this way we are connecting all the ages with similar weights possible. So basically that's all for the question. Now I'll be heading to the follow-up questions. I'm asked that in what real-world ML scenario I would consider taking MSTs, example like sensor network, feature section, etc. So basically, suppose I have hundreds or thousands of sensors collecting similar data, example like temperature, humidity. So in this case, many sensors can give almost identical readings. So it's a storage loss, it's a power loss. So using all sensors in your machine learning model is wasteful and slow. So what we can do here, so MST is a solution for that, as it's reduced redundancy. Think of like the sensor is a node, and the weight that is similar, it's a age weight, like this way. So for that we have to take the MST in way that connects sensors in a most efficient way, like a minimum total similarity, and to help identify typical representative sensors. So without MST, so to sum up in short, like without MST there will be too many sensors, so the data will be repeated, and there will be high storage and training cost and redundant ages. But with MST we can only take the necessary ages and the lowest weight possible. So in one line, yes, in real world ML scenario like sensor network, I have to consider this, as it will make the network efficient and faster in ML training. To sum up in short, Bharovkar algorithm helps to find an MST in a distributive system by having each node locally pick its cheapest age, and MSTs are useful in machine learning model as it can connect sensors efficiently and selecting only the most informative ones, so it is not wasting the storage. Okay. Now the last question is the question 4. So the question was for a tree or graph-based feature index in a memory constrained environment, compare slab allocation versus garbage collection as memory management strategies. So first of all, What is a feature index? Basically, a feature index is a data structure used in machine learning systems to store and quickly find features like user data. As I am given a memory constrained environment, that means the RAM is definite and limited. Also, it's a tree or curve based feature index. So in here, to compare slab allocation versus garbage allocation as memory management strategies, I have already wrote some advantages and disadvantages. Now I'll be talking about that. Basically, a slab allocation means pre-allocating fixed size memory blocks for objects of the same type. Uh, suppose this can be a pre-allocated memory. Similarly, I can have as much as I want. Like this. Similarly, I can have as much as I want. So for example, I can say, imagine that a tree node has 128 bytes, and I created a big pool called a slab of memory divided into small boxes like I have created in here, which is 128 bytes each. So whenever I'm adding a new node, I take one free boxes and add it there directly. Like I'm adding the data here directly. So when I deleted a node, I put that box back. So for that, the advantages is like allocation and deallocation is in order one. So I don't have to search for free space or space to the operating system every time. Free slots are already waiting for me as I am creating at the beginning. So allocating or freeing the memory takes constant order one time, so it's super fast. Also, it's cache friendly, so all objects are stored close together in the memory, so which makes it easier for CPU cache to access them efficiently. So lookups are always faster, and no fragmentation is happening here, as I'm directly adding the data similar to this size inside basically inside a slab. All blocks are equal in size, so no space is wasted, so everything stays compact and clean. Here comes the disadvantage regarding that, as it's less adaptable. Slab allocation works great if all objects are in the same size. Suppose if that I have took 128 bytes each slab allocated blocks, but if it's more than 128 bytes, then it's not gonna fit in here. The memory overhead, as I might allocate more slabs than it actually need, just to be ready for future use. Like I'm creating more in here, but that means it's full of memory wastage if I'm not adding anything in here later. Internal fragmentation can also occur. It's as if even inside a slab, some slots may stay empty if not all are used. Those empty slots are internal fragmentation memory that's reserved but idle. Now, after discussing this whole, moving to the garbage collection. Garbage collection is automatic memory management that usually used in Java or Python. This system basically automatically tracks which objects are still in use and which are not. Like basically, it's a tracking mechanism that which is used and which is not. So when it finds unused object, it frees the memory automatically. So you don't have to manually free memory with the function called free or delete. The garbage collector In short, basically automatically manage the memory and unused items. So it's a cleaning mechanism that periodically recovers anything if it's needed. As the advantage here, I can say that it has improved the use of memory, as it's constantly scanning for memories and free spaces, so that isn't used anymore. This prevents memory leaks and ensures efficient reuse. Also, it manages complex object graphs, like in many programs objects just reference each other, like a is connected to b is connected to c. It's hard to human to manually track each one, like from the beginning to the last to delete. So garbage collector automatically figures out what's still connected and needed and what's not, as it's basically checking every time. And last but not the least is flexibility in allocation patterns, as I can freely create and delete objects whenever I want. That means no manual cleanup needed. Garbage collector basically handles it for the user, making the programming easier. But here comes some disadvantages, as it has unpredictable pauses. Basically, the garbage collector sometimes pauses the program temporarily to clean the memory, which is a pure overhead. These pauses can happen at unpredictable time, which is bad for a real time or latency sensitive system. Suppose like a system that needs real time data, or we have to update the data in latency sensitive way, like simultaneously. So it's a issue in here. Second one is it is increasing the overhead, as I have talked about the unpredictable process. It's can clear that it is increasing the overhead, as CPU is taking extra time to track which memory is used or which is not. So the non-deterministic latency means that the latency is unpredictable, as I'm sometimes blocking the CPU times to just clean up the process. So it's the latency time is not deterministic. So to sum up that, now I'll be discussing about the follow-up section. The follow-up question is, which option is better supports predictable latency for online serving in machine learning system? To me, slab allocation is better, and I have reasons for that I've discussed in here. Now I'm going to discuss about it here. So in online serving machine learning model, that means I'm using a recommender system like a search engine or chatbot, or previously that I've talked about, like Netflix, Spotify. Then this model must serve prediction instantly in real time. So whenever a user makes a request, that means the API request must be processed fast, consistent, and with no unexpected slowdowns. Suppose a user is clicking like show me recommended movies, like I have discussed about in Netflix. So the model must respond in milliseconds, not pause, because it's cleaning the memory in garbage collection. But in slab allocation, it's like there isn't any cleaning mechanism for that. So no garbage collection delays, as slab allocation doesn't have garbage collection. So there are no random cleanup pauses, and it's predictable timing. Like if the allocation and deallocation always takes the constant time, like order of 1, ensuring the predictable latency. Then again, it's cache friendly, as memory is stored neatly in continuous blocks, which makes the CPU cache access faster. Then ideal for uniform projects, like in machine learning systems use fixed size data like embeddings or tree nodes. So it's perfect for slips. And Why I'm not considering garbage collection here, that I have reasons for that too, as it's pausing every time, so it delay the prediction responses, so that for user experience, and there are unpredictable timing, like I can guarantee that consistent latency per request, so it's pure overhead, and extra processing can slow down the machine learning computation. So therefore, for online machine learning serving systems, while latency must be consistent and predictable, stable allocation is better than memory management strategy. And I have given the example for that about the Netflix and YouTube. So that's all from me. So here I'm summing the whole set A questions. Thank you.